Gnanam paramam dheyam. Knowledge is supreme.
So far we have talked about rotational spectra, microwave spectra, and we have talked about vibrational spectra, that is IR spectra, right. Today we are going to talk about what is called rho vibrational spectra. Of course, anybody who has studied say Hindi grammar would know that we are very good at joining up two words and making one word out of two. So, this is one such word, not in Hindi but in English. Rho vibrational spectrum, obviously it means a spectrum that has signatures from vibrational as well as rotational levels. So, if you remember in the last discussion we had said that for a harmonic oscillator you expect your spectrum to look something like this, right, a single line, allowing for line broadening, which we are going to study in a little more detail later on, and allowing for some noise in the detector that we talked about very briefly in one of our earlier classes. You might expect this spectrum to look something like this. However, if you have a good enough spectrometer, then the spectrum actually looks like this. This here is an experimentally recorded high resolution IR spectrum of HCl. HCl fits our bill, right. It has a permanent dipole moment. So, if there is a vibration, that dipole moment is going to change. If you remember, one condition for observing IR spectrum is that d mu dx at equilibrium position must be equal to 0. That is of course satisfied by HCl. And when I say high resolution, how high resolution do I mean? Of course, unless your eyes have really very high resolution, I do not expect you to be able to read what is written on the x axis. Let me see if I can. So, the x axis reads something like 3000, this is 3000, this is 3050, and the small marks are like 10 centimeter inverse, separated by 10 centimeter inverse each, alright. So, that is the kind of resolution you need in order to see this kind of a fine structure. Why do we see this kind of fine structure? We see it because if I zoom in to your harmonic potential energy surface, let us say I want to talk only about V equal to 0 and V equal to 1. Let us zoom into this part only. Now, you understand that for each of these vibrational levels, the molecule can have as many rotational levels as there can be, right. So, V equal to 0 would be associated with, I can call this J dash equal to 0. What is the smallest value of J dash? 0 or 1? 0, right. Then J dash equal to 1, J dash equal to 2, and so on and so forth. I will just, of course, this is a very, this figure is not to scale, right. This separation may be about 1000 centimeter inverse. These separations would typically be about 10 centimeter inverse or so. Similarly, this one I can call this J double dash is equal to, we can say 0, J double dash equal to 1, J double dash equal to 2, and so on and so forth, alright. And as you know, the energy spacing of rotational levels is such that it is not as if only J dash equal to 0 will be populated. See, between V equal to 0 and V equal to 1, at room temperature for most cases, we can say without worrying too much that only V equal to 0 is populated, right. We discussed that earlier. For 1000 centimeter inverse energy gap, the population of V equal to 1 is 8 if the population of V equal to 0 is 1000. So, practically all molecules are at V equal to 0, not so for the J levels, right. So, in fact, as you know, all these J levels will be populated, and the population distribution, if I can draw a 90-degree rotated curve, would be something like this. Right, but these are the different J levels. Remember this? We had discussed this in light of Boltzmann distribution, 2j plus 1 multiplied by e to the power minus delta Ej divided by kT. Remember, one J max had the maximum value, and I think you know the expression, or you can work out the expression for that J max value, right? What is it? Root over kT by 2hc minus half. Is that right? Yeah. You don't have to remember this. I will not remember this after maybe a month or so, I am sure. So, there is a population distribution here. So, now when you talk about say an upward transition, that upward transition can begin from any of these J levels, isn't it? What about this level? Is it populated at room temperature? No, because this J level is associated with a higher vibrational level, right? So, because it is associated with a higher vibrational level, there is no population here. But then here, since all these are populated and it is not J dash equal to 0, that is a maximum population, there is a population distribution like this. So, now you can understand transitions can begin from any of these levels, alright. The question is, where do they terminate? Is there some selection rule for this, or is there no selection rule? Okay, and we are going to do this in two kinds of scenarios, one in which Born-Oppenheimer approximation holds and the other in which Born-Oppenheimer approximation does not hold, alright. To start with, we are going to stick to our selection rules, delta V equal to 1 and delta J equal to 1. Of course, if Born-Oppenheimer approximation holds, then it is not very difficult that these selection rules are going to hold as well. What does Born-Oppenheimer approximation say? When you talk about one kind of transition, you do not have to worry about the other kind, right? That is Born-Oppenheimer approximation deconstructed and put in very simple language, okay? Which means you can treat the vibrational problem separately, rotational problem separately. From there, this thing kind of follows, but we will not derive it. We will just go by this. So, first situation, we say when Born-Oppenheimer approximation is valid. Do you have questions? Okay. So, if Born-Oppenheimer approximation holds, what does that mean? That means the vibration does not affect the rotational parameter, right? What is the rotational parameter? B. So, for so, no matter whether you work with V equal to 0 or V equal to 1, B is the same, alright. So, if that is the case, what is the energy say of V equal to 0 and J equal to J dash? It will be a sum of the vibration rotation energies, right? What would that be? If you remember, and when I write epsilon, what do I mean? Do I mean centimeter inverse or do I mean joule? I mean centimeter inverse. So, what will be the vibrational expression, the expression for vibrational energy be? Nu bar vibration, let us say, multiplied by V plus half, right? Right now we are working with harmonic oscillator. So, for when V equal to 0, it is going to be half nu bar, and I will write nu bar Vib, but in a previous discussion you might remember we found out something interesting about this nu bar Vib. What is that? Frequency of vibration is equal to, yeah, frequency of something else. Yes, frequency of radiation, right? So, frequency of radiation is equal to frequency of vibration. So, if I just wrote nu bar light, that would also be valid, okay, right, plus B J dash into J dash plus 1. Achha, let us start with the delta J equal to 1 case, the delta J equal to plus 1. What would be the range of J dash in this case if delta J equal to plus 1? J dash is the level of origin, J double dash in my notation is level of destination. So, if delta J equal to plus 1, what are the allowed values of J dash? This might sound like a trivial question at this point. Is there a question? Is there an answer? Achha. That might be a right answer to a different question. My question is, if for delta J equal to plus 1, J dash of course is the vibrational levels of V equal to 0, and I am working with delta J equal to plus 1. So, what is the range of allowed values of, or I will make it simpler, what is the minimum value of J dash I can take? 0, plus 1. If it was minus 1, now let me go to the next situation which we will revisit in a while. For delta J equal to minus 1, what would be the minimum value of J dash that I can use? Then it would be 1, right? Because if it starts from 0, there is no minus 1 level here, okay, but we will come to that in a moment. Let us get done with this. So, range of J's, let us not forget, J dash is equal to 0, 1, 2, so on and so forth. Okay, so far so good. Then what is epsilon 1 J double dash? That would be half nu bar Vib plus B J double dash into J double dash plus 1. But then I know already that delta J equal to plus 1. So, J double dash can be replaced by J dash plus 1, isn't it? So, yes. Oh, sorry, 3 by 2. My mistake. That is right, V plus half, right? I forgot the V part. I was so engrossed with J that I did not think about V. You are right. It is 3 by 2 nu bar Vib plus B into J double dash plus 1. Okay. So, can I write instead of J double dash, can I write J dash plus 1? So, this thing becomes J double dash plus 1 multiplied by J dash plus 1 multiplied by J dash plus 2. Is that right? Is there a question? No question? Sure? Simple? So, in that case, what is your, how do I write it? Let me write it as nu bar, right? Nu bar for delta J equal to plus 1. What is that going to be? Epsilon 1 J double dash minus epsilon 0 J dash. What does that turn out to be? That will be nu bar Vib plus B. I can take J dash plus 1 common, right? And then I am left with J dash plus 2 minus J dash, that will be 2. So, nu bar for delta J equal to plus 1 turns out to be nu bar of vibration plus 2B into J dash plus 1. Clear? Simple? Are we ready to go to the next one, delta J equal to minus 1? So, I wrote delta J equal to plus minus 1 earlier anyway. So far we have discussed delta J equal to plus 1. Now, we will talk about delta J equal to minus 1. Now, if delta J equal to minus 1, what is the range of J dash you said? 1, 2, 3, so on and so forth. But then if I use that, I am going to get an expression that will look different from this. Also, I want to maintain the same range. So, what I will do is, I will not work with J dash, I will rather work with J double dash. Is it okay if I write J double dash equal to 0, 1, 2, so on and so forth? Okay. The minimum value of J dash is 1, but then from there you can have a transition from here to J double dash equal to 0. So, if I work with J double dash in this case instead of J dash, then I can keep the same range as I did in the previous statement. That is why I work with J double dash. Are we clear what is going on? Okay. So, now how do I write it? So, we are talking about this J dash to J dash minus 1, or in other words J double dash plus 1 to J double dash kind of transition, isn't it? Okay. So, I am going to write this in terms of this j dashed now is j double dashed minus 1. So, sorry, j double dash plus 1. How do I write it now? I can write it as j double dash plus 1 multiplied by this becomes j double dash. Is that right? What about this? This becomes the simpler bj double dash multiplied by multiplied by j double dash plus 1. Okay. What then is nu bar for delta j equal to minus 1? I think I have been able to confuse some of you at least. Yes? Which should be plus 2? You are right. You are right. J double dash plus 2. What am I doing? This is okay. This is j double dash plus 2. You are right. Is this expression correct? Now, when I subtract one from the other, what do I get? I get similar something. Here, the only difference is this becomes j double dash, this becomes minus, and the range remains the same as what the range was for j dash 0 onwards. Okay. So, I can write a general expression for nu bar to be nu bar Vib plus minus 2b into j plus 1, where j equal to 0, 1, 2, so on and so forth. Is that correct? Is there a question? Okay. So, minimum value of j is 0. So, when you put j equal to 0 here, where level of origin or level of destination is equal to 0, what do you get? You get nu bar Vib plus minus 2b, right? What does that tell us? That tells us that there will be no transition at nu bar Vib. The wave number where you expect to see a transition, there will be none. Rather, there will be transitions on the two sides. Okay. So, that is what you see there. Let us say this is your nu bar Vib. There will be nothing there. Where will be the first transition on the higher energy side? J equal to 1. So, j equal to 1 means what? Sorry, j equal to 0. J equal to 0 is plus 2. And what about the other side, lower energy side? Minus 2b, right? So, the first line is going to occur at plus 2b, and here it will be minus 2b. So, this separation is going to be 4b. All right. Where will the next line occur? 2b on that side? No. So, basically this is 0, this is 2b, this will occur at 4b. So, 4b minus 2b is 2b, right? So, what you get essentially is you get two wings, each of which is exactly like the rotational spectrum of the molecule, one on the higher side, one on the lower side of the frequency, where which represents the energy difference between V equal to 0 and V equal to 1, 0 vibrational levels. Okay? That is what you see experimentally. Are we clear so far? Okay? What do you expect to see? You expect to see equispaced lines on both sides. Whether you see that or not, we will come to that in a little while. But before that, I would like to draw your attention to one thing. if you look at this closely, if you zoom, this we have discussed, if you zoom into one of these lines, then what do you see? Can you see from here that it does not look like one line, right? In fact, if you have a good enough resolution, this is what you see. Each line, remember this is HCl and we have discussed this already. Yeah, exactly, it is an effect of isotope. Okay. So, you have two lines, one for Cl35 and one for Cl37. So, if you have a good resolution in your IR spectrum, then not only you can tell what the bond strength is, you can also say what is the bond length, and you can also get an idea of isotopic abundance. Okay. Of course, we are saved by the fact that in case of hydrogen, deuterium, tritium, etc., do not have so much of abundance. If they were also almost equally abundant, then what would happen? Each line would have had a more complicated structure. Okay. It would not have been a doublet, it would have been multiplet. Each line would have been a multiplet consisting of smaller lines, but then you could get more information out of it as well. Okay. Is there a question so far? No? Then I want you to look at the spectrum a little more closely. What is the expectation? The expectation is that on both sides, oh by the way, before I forget, the lower energy side, this is the lower energy side, this is called the P branch, and the higher energy side you call it not Q but R branch. If you had a line right here, then you would call that the Q branch. Okay. Please remember, this P is lower energy and R is higher energy than what is expected if you do not have this rotational fine structure. Okay. Now, from the simplistic picture that we have developed so far, we expect that in this P branch and Q branch lines should be equispaced, right. Now, I ask you to look at this a little more closely. Look at these and look at these. Are the spacings really equal? No, right? They are not equal. So, the question is, why are they not equal? They are not equal because so far we have worked under the ambit of Born-Oppenheimer approximation. We have assumed that Born-Oppenheimer approximation holds. That is not necessarily the case. It is possible that there is a breakdown of Born-Oppenheimer approximation and vibrations and rotations actually talk to each other. Okay. Let us see what happens when vibrations and rotations talk to each other. Let us see what happens when Born-Oppenheimer approximation breaks down. So, if Born-Oppenheimer approximation breaks down, B is not going to be the same for the two vibrational levels. So, let us define like this: B is equal to B0 for V equal to 0, B1 for V equal to 1. Okay. And let us start with once again delta J equal to +1. I will have to reset all this. B0 J dashed into J dash plus 1. This one is B J double dashed into J double dash plus 1, and we are talking about delta J equal to +1. So, the range of J dashed is 0, 1, 2, so on and so forth. All right. This I have to write B1. Please remember this expression. When we considered that Born-Oppenheimer approximation holds, we had something like nu bar Vib plus minus 2B into J plus 1. Okay. So, what is nu bar? This minus this, that will give you once again nu bar Vib plus, this time we have a little more complicated scenario, right. I have B1 as well as B0, okay. And Of course, whoever has appeared in competitive exams involving maths is master of manipulations, I mean mathematical manipulations, right. So, it is not very difficult for you to try and play around with this result and write it in a form that looks nice. And one of the techniques that you learn while doing mathematical manipulation is that we should try and collect all the terms in the same power of something. Okay. Here you are going to have what j dash square j and j dash and so on and so forth. Let us try and collect them, collect the same powers, and let us see what kind of result we get. But before that, once again let us write the second one in terms of j dash. Here again j dash goes from 0 onwards. So, this again becomes j dash plus 1 multiplied by j dash plus 2. Is correct? So, let us first collect the terms in say j dash square. What do I have? B1 minus B0 into J1 square into J dash square, is that right? And now the remaining course is kind of defined. We have to try and find terms in B1 minus B0, okay, right. Now, if I look at the terms in J dash, what do you have from here? You have B1 into J dash, sorry, B0 into J dash, right. From here, what do you have? 3B1 into J dash, okay. So, now the thing is, since I have J1 dash square, x square, whenever we have x square, the first formula that comes to our mind is x square plus 2ab plus y square. What am I doing? X square plus 2xy plus y square, right. So, let us see if we can write it, and since we already have this 3ab term, let us write it as, I am using xy and ab reversibly, that is not good. Since we already have this 3xy term, let us see if we can write it in as say xy 2xy plus xy, okay. So, this is basically what 3b1 into j dash, right. I will write it as 2 plus 2j dash into b1 plus j dash into b1. I hope nobody has an issue with that, okay. Now, what else do I have? I have b0 into j dash. So, I will write it like this, 2j dash b1 minus b0. Then what do I have to write here? J dash into b1 plus b0, right. What, is that so difficult? What do I have here? I have b0 into j dash, okay. What do I have here? 2j dash minus 2j dash b0. Am I making a mistake somewhere? Yeah, is okay, right? Okay. Then what am I left with now? What is it that I have not written? 2b1, right? I will write it like this, plus b1 plus b1. Here I will write minus b0, here I will write plus b0. Done? What do I get then? I get nu bar Vib plus, so what was the expression I had for delta j equal to plus 1 earlier when Born-Oppenheimer approximation held? What was the expression there? Nu bar Vib plus b, 2b into j dash plus 1. So, what I can do is I can write it like this, b1 plus b0 into j dash plus 1 and plus j dash plus 1 whole square multiplied by, I have written it in a little strange manner anyway, plus b1 minus b0 multiplied by j dash plus 1 whole square. Does this make sense? Maybe I will write it here. Nu bar is nu bar Vib plus B1 plus B0 into J dash plus 1 plus B1 minus B0 into J dash plus 1 whole square. What is the range of J dash? 0 onwards, right? So, this is the expression I have. Now, do we see is this expression, does it have any resemblance with the expression we had when Born-Oppenheimer approximation held or not? When Born-Oppenheimer approximation held, what was it? Nu bar Web plus 2b into J dash plus 1. This third term was not there. Now, see, Born-Oppenheimer approximation holding means what? B1 should be equal to B0, then that would become 2b anyway. Now, since Born-Oppenheimer approximation does not hold, that 2b has become B1 plus B0, and we have another term B1 minus B0. Now, do you expect B1 and B0 to be very, very different from each other, or do you expect them to be well close to each other? Not equal, but close to each other, right? Close to each other, that is what you expect. So, in that case, this term is actually small, isn't it? When does it become important? It becomes important for large values of j. Did I say all that a bit too quickly? What I am trying to say is this: B1 and B0 you told me are close to each other. B1 is B0 plus some delta B. Okay? So, this first term, if we consider B1 is equal to B0, the first term gives me exactly the same expression as what I could get if Born-Oppenheimer approximation held. This one is the correction term. Well, there is already some correction here. Instead of 2b, I have written B1 plus B0. But this third term is really the correction term that comes in the energy, and that is B1 minus B0 multiplied by J dash plus 1 whole square. B1 minus B0, as you told me, is small. So, this term, well, not second, the third term that comes in as a correction, that is going to be important only for large values of j. Okay? If you look at this spectrum, in which part of the spectra do you have contributions from large value of j? In the middle, on left hand side or right hand side? Yeah? Left hand side means, your left hand means this one, right? What about the right hand side? That also has contribution for high values of j. So, if you look at the high end of the spectrum, high energy end of the spectrum and the low energy end of the spectrum, that is where you expect to see this deviation from what is expected when Born-Oppenheimer approximation holds. If you look at the center, say look at these two lines and look at these two, they are more or less the same, right? The spacing is more or less the same. That is because j values involved are small, and since B1 plus B minus B0, B1 minus B0 is small anyway, you do not see so much of effect of Born-Oppenheimer breakdown in these regions. In the high energy end and the low energy end, that is where the effect becomes prominent, and you see that the lines are definitely not equispaced anymore. All right? Understood? So, this is what you see when Born-Oppenheimer approximation breaks down. Is there any question so far? Yes. How can we determine how many rotational levels will be there for a vibrational level? In principle, there are infinite. But then what matters is how many rotational levels have some sizable population. That is determined by that 2j plus 1 multiplied by e to the power minus delta E by kt. If you remember, 2j plus 1 of course is a line, and the other one is an exponential decay. So, wherever this becomes almost 0, it does not matter that 2j plus 1 takes a large value, the product is still a 0. Okay. So, that will depend on B. What is the value of B? If the value of B is small, then what will happen? Many higher levels will be populated. If value of B is large, then higher levels will not be populated to that extent. This fall off of the exponential part is going to be very fast. So, it depends what your B value is. Good question. Any other question? Right. Of course, we have done only half of the problem. I ask you to do the remaining half. And since today I have already made, I think, 2 or 3 mistakes in algebra, I will ask you to do it yourself. What am I asking you to do? Please work out the expression for delta j equal to -1. Same strategy, right? Delta j equal to -1. Now you work not with j dash, but with j double dash, because then you can keep the range the same. Work it out, you will see that this is what happens. This part does not change. No, sorry. This is what happens. Okay, the correction term does not change. It is still plus. It's not minus. Okay. Please work it out yourself. You will see that the minus will come here, like what it did in the earlier case, but in this B1 minus B0 term, it will still remain plus. That I leave to you as homework. And if you want to, this is worked out in Manuel's book, not in as many steps, but you can at least get the final result. Okay. So, you can study this part from Manuel's book. Any other question so far? If not, we conclude our discussion on row vibrational spectrum.